Lecture 31, Inductors in Series and Parallel. The objective of this lecture is to understand how multiple inductors behave when they are connected together in a circuit. So let's start with inductors in series. So inductors are said to be in series if they are connected one after another, just like this, and the same current flows through every inductor. So the key observation is the current is same through every inductor and the voltage is distributed. So let's derive the condition for equivalent inductance. So for the three inductors in series, current is same. Therefore, rate of change of current will also be same. And voltage is distributed. Therefore, net voltage is simply equal to V1 plus V2 plus V3. So on substitution, we know that V is equal to L di by dt. Therefore, V1 is equal to L1 di by dt. V2 is equal to L2 di by dt, and so on. So therefore, this equation becomes L di by dt will be equal to L1 di by dt plus L2 di by dt plus L3 di by dt. And this L is nothing but the equivalent inductance. So from here, di by dt is cancelled out and L equivalent will simply be equal to L1 plus L2 plus L3. So this is the general formula for equivalent inductance in series. So one key observation is the equivalent inductance in series is greater than the largest of the individual inductor in the group. So let's move on to inductor in parallel. So inductors are said to be in parallel if they are connected between same two nodes. So here there are two nodes A and B. All the entities are connected between A and B. The same voltage appears across every inductor. The key observations are voltage is same, but the currents are distributed. The total current will be simply, that is I total will be simply equal to I1 plus I2 plus I3. So this is I total is equal to I1 plus I2 plus I3. Taking derivative on both sides, we get di total by dt will be simply equal to di1 by dt plus di2 by dt plus di3 by dt. So we know that the voltage is simply equal to, that is L equivalent di total by dt, and from here di total divided by dt will be simply equal to V by L equivalent. So using this relation, we can replace this equation with V by L equivalent is equal to V by L1 plus V by L2 plus V by L3. And from here, 1 by L equivalent will simply come out to be 1 by L1 plus 1 by L2 plus 1 by L3 plus so on. And this is the general formula for equivalent inductance in parallel. And from here we can see that the equivalent inductance is less than any of the individual inductance present in the parallel. Finally, let's move on to the comparison. Current in case of series connection is same and in parallel connection it is different. Voltage in series connection is different and in parallel connection is same. Formula is simply L equivalent will be equal to L1 plus L2 plus L3 plus so on. In parallel it is 1 by L equivalent equal to 1 by L1 plus 1 by L2 plus so on. And the energy stored will be half Li square. So since equivalent inductance increases, therefore energy increases, and here in parallel connection energy decreases, and the final result is the equivalent inductance increases and here the equivalent inductance decreases. So solving these examples using these results, 1 by L equivalent will be equal to 1 by 4 millihenry plus 1 by 2 millihenry plus 1 by 4 millihenry, and from here L equivalent comes out to be 1 millihenry, and in this case the inductors are in series. Therefore, the net inductance will be sum of all three, that is 4 plus 4 plus 2, that is 10 millihenry.